Okay, so question 2. We've got a single load on a beam, a quarter length along the beam, and we basically just got to integrate it and find the deflections. Now notice this question includes lots of algebra, which I'm going to, and it's mentioning constants as well. I'm looking for the formula here. So on your formula sheet, you've got these two equations. But not what I'm going to use. I'm going to go back to the derivative, second order derivative. So you can state that bring the EI up with left hand side equals mx. So this is our starting point really, for a problem like this. The other thing I'd be tempted to do, but I'm not going to do it this time, would be I'd be tempted to set L to be, I don't know, let's say 4s, and then you can say that your L over 4 equals s, and use S as your variable and avoid the fractions. But I won't do it for this solution. So for part B's and C's, it's saying determine the bending moment between those sections. So what I'm going to do is I'm going to use the Clory's method, and I'm going to tell the exam marker that that's what I'm doing there. Okay, so let's make a start. So for part A, the reactions. It's something that you could almost do in your head, because it's a proportionate thing, isn't it? So the reaction at A is going to be 3/4 of the load, and the reaction at C will be 1/4 of the load. But to do this formally, we would, let's say, take moments at A, and our load is value P, so that would be give me PL over 4, and then I've got a reaction here, RC, and a reaction here, RA, so that would be minus L times RC equals 0, therefore RC equals P divided by 4, and then I could sum forces in the y direction. So RA, take away P, plus RC equals 0. So that therefore tells me that RA equals P take away RC, so that gives me 3/4 P. And then what I would do to speed things up, I would say saying determine the bending moment B and C are solved using Maclaurin's method. And so that has simple, that has just one equation then. So M is going to be, what you need to do for this is that you imagine that you're going to take moments just a little bit inside from the reaction here. So we're going to take a moment from this point here. So we're at distance x from there. And we're going to go around like that. And need to be a bit careful in terms of how you define your M's. I've probably gone the wrong way. If we were doing this as a first year problem, we'd be going in an anti-clockwise sense, but I think in the second year we've switched convention, and I think we go in a clockwise sense. So M will be what we'll be taking at this pivot here, is what we're going to be taking our moments around clockwise. So I think that's valid for this year. But I think it'd be wrong if we was doing this as a first year problem. At least we got the signs wrong. It doesn't really matter much. What it's saying is that when we end up with our deflection Y, we would be expecting obviously this thing to be sagging. So if I get a positive number for Y when it's in the middle, then I know that Y is being defined pointing downwards. And if I get a negative number, then I know Y that the negative number is Y is going upwards, as it were. So therefore the beam's deflecting downwards. Anyway, it doesn't really matter. So let's take moments at this arbitrary X position and look back at the forces that we've got. So the first one we can see is that we've got a RA. Now, when you times by your X's, you want to put your distances into triangle brackets. The exception is really when X starts at the initial position. But to be consistent, you won't see this in textbooks, but to be consistent, I'm going to put the X in a triangle bracket. Okay, and the other one will be that the force is going downwards. So you can see that this is going clockwise. So this force is, if we take this to be your pivot position, that's force is going downwards, so that's going to be minus the force is P. Distance from here to here I need to measure. Well, I know that the distance from here to here is X, and we've got this distance here, L divided by 4, so we need to take off that distance. So we're going to have X take away L divided by 4. So if you haven't seen the Maclaurin's method before, these triangles, brackets, basically mean if the thing inside the triangle brackets is less than 0, then the value the bracket is equal to 0. So let's say we've got something inside, let's call it f. So if f is less than 0, therefore the bracket equals 0. If f is greater than 0, then the bracket will equal whatever the value of the bracket is. So that's the Maclaurin's method rule. Okay, not quite finished because I want to replace my RA with a P, because we need to do this in terms of P, X, and L's. So that will be 3 over 4 P X, take away P X minus L over 4. Okay, so that's done parts of B and C. Express the slope. So to find the slope, we're going to be doing this equation here. And I will keep my E and I on the left-hand side. So E, I, I'm going to integrate this equation once. So the left-hand side becomes first order differential. And on the right-hand side, we need to integrate our mx function. So let's put that mx function in. Open a bracket. Got p here, so we could bring the p out. So I've got quarter x. Now with the Maclaurin's method, you're never allowed to expand out your brackets. But other than that, you treat them as if they're normal brackets. Close that bracket there. And we're going to integrate this with respect to x. So if I integrate something which has got x inside the brackets, leading term there, then all I would want to do, and if I didn't want to expand out that bracket, all I'd want to do therefore is would be to integrate that as if it's kind of x. So here, if we integrate the terms, we're going to get first one. Let's integrate our bracket here, so that takes it to the power 2, because we're currently at the power 1. 2, so it means I have to divide through by 2, so that becomes 1 over 8. Next one, minus, so we're going to integrate the bracket here. So initially that's to the power 1, so take it to the power 2, so it means we have to divide through by 2. And then we're going to have our first constant, C1. Okay, so that's part D done. Right, so part E is find the deflection. So what we're doing here is we're integrating this again to find y. E over I. It's tempting to bring the p over to the left-hand side, so we've got over p. So integrate the delta y over delta x. First order differential just becomes y. Let's put in a note that we know it's a function of x. Now we want to integrate all of this thing in the bracket. Okay, so let's do that. So we've got first one, we're going to raise this to the power 3. So 8 times 3, 24. And this will come to the power 3, so that's 1/6. C1, need to integrate that with respect to x. So put an x there, and then we're going to finally have our integration constant C2. And that's it. So that's part E done. We found an expression for the deflection, which is the y term there. Calculate the integral constants. So that's for part F. Right, so what I'll do is I'll write this down again and copy it to the next page. So the alternative method to solve this problem is to use the stitch-up method, where didn't copy. So the stitch-up method, let's just talk about that before I finish the question. Stitch-up method means that at this particular point here, I need to apply 2 boundary conditions. The first boundary condition is that when I integrate up to the B point, I'm going to get an equation for my y up to that point there. And we're at B. And that is going to have to equal the equation right of that point there. So that would be the first boundary condition you'd need to apply. And your second boundary condition, of course, is the fact that the slope just left of B, which let's indicate slope by doing it as an arrow, is going to be the same as the slope just right of B. Now, the problem with that is that it produces a lot of algebra and quite a tedious amount of work to do. And the advantage with this Laplace method is that you can solve the problem about half the time. So the final thing is that we've been asked to find the constants. So what boundary conditions do we have for using the Maclaurin's method? Well, the only boundary conditions we have can be applied to the final equation that you've got here, which is your deflection. So what do you know about your boundary conditions for your deflection? Well, I know that when y is at 0, we've got no deflection. So I imagine that we're going to get some deflection like this. And I know when we are x equals length L, we're going to have no deflection. So here. So they are my 2 boundary conditions I'm going to apply. So boundary condition 1. So that would be the one on the left. X equals 0. And now let's substitute in our 0 into all of these terms. Remember our rule. So our rule is that if, well, obviously that's a 0. If the inside in this bracket is less than 0, this term becomes 0. So that's a 0. And a 0 times C1, so that's going to be a 0. So your C2, and where is the position when y is at x equals 0? 0. So therefore, C2 equals 0. Boundary condition 2. And we are when the other end of the bar, so when x equals L, I'll substitute that in. So I've got L take away a quarter L, so that leaves me with 3/4 L. And I've previously found that C2 is 0, so I'm not going to substitute that. So here, left-hand side is 0. Now we can convert our triangle brackets to ordinary brackets because we know that the things inside the brackets are more than 0. The f is greater than 0, therefore the bracket becomes the f value. That's the Maclaury's method. Okay, so we've got 1/24 L to the power 3. I think I'm going to use a calculator to solve this. 3 divided by 4 to the power 3. So minus 6/27 over 64 L to the power 3. And then I've got C1 L. So notice I need to divide through by L here and tidy up a little bit. So 0. So that's going to leave me with, let's use the calculator to do the work for me. 1/24 take away 1/6 times by 27 divided by 64. So that's minus 11384. So my L to the power 3 is going to become L squared plus C1 because I've divided through by L. And let's just present the final answer. C1 therefore is going to be 11/384 L squared. Okay, so that's done. You could, if you wanted to, actually go back and find what the equivalent of C3 and C4 would be if you're doing the stitch-up method. That's not required, but how you would do that would be basically looking at this equation twice. So the next bit is not required, but I just want to explain to you how you would go about finding C3 and C4. So what you basically do there is say, okay, so I've got EI over P. I should copy it. I should probably already that. So for AB, I can say that we've got EI over P, and I'm going to apply the fact that that I know that for this particular section that x is less than y over 4, L over 4, sorry. So here we know if we substitute in the value of x less than that, that this will still be a positive number. So 1/24th. And then convert your triangle brackets to a curved bracket. Here, if you put in x is less than L over 4, this becomes a 0. So that term we ignore. C1 we calculated previously to be L 11 over, well, it's up there, okay. We calculated to be plus 11,384 L squared x. And C2 we calculated to be, I got that right? Yeah, C2 we calculated to be 0. So that is that for that section. So I can see now that we're defining y to be going downwards in my convention. For BC, slightly more interesting here. So here we've got the case that x is greater than L over 4. So this bracket in this case is going to become a positive. So you've got 1 over 24 x to the power 3 minus 1/6 x over 4 to the power 3. Okay, my C1 is 11 over 384. That number doesn't look particularly nice to me, so I'm a bit worried whether this is correct. Okay, L squared x, C2 is 0. So what you need to do next would be to expand out this bracket here. The only way I can do that would be using Pascal's triangle. Like that. So that gives me 1 over 24 x to the power 3 minus 1/6. And we'll expand out the bracket. X to the power 3. And then I've got, that's going to be negative. And that's going to be 3 over 4 x squared L. And the next one will be plus 3 So we've got 4 times by 4, so that would be 16 x L squared, making sure the powers always add up to 3. Okay, and then the final one will be a negative 4 to the power 3, 64. L to the power 3 plus 11, 384 L squared x. So you want to bring your x to the power 3's together. So we've got 1 divided by 24. Take away 1, 6. So that becomes minus 1/8 x to the power 3. Let's bring our x squares together. The only one I've got is this term here. So that is minus 1/6 times by minus 3/4. We're going to be positive. So plus 1/8, and that will be x squared L. And things a bit more interesting for x's, because these two things need to be combined. So we've got 3 over 16 plus 11 divided by 384. So that is, oh no, did I make a mistake there? So I've got a minus 6. And did I make a mistake there? No, I didn't. I combined that. So we've got minus 1/6 times by the 3 over 16. As I say, you don't have to do all this. This page is not required, but it's interesting to do, just show you how you'd get the 3 and the 4 constant. Okay, so that's that thing times by that thing. Okay, and then we want to add on this term here, plus 11 divided by 384. So that's minus 1384 x L squared, and then we want to do the final term here, so it's going to be this times this, so that would be a positive. So what's 64 times by 6? Okay, 384 again, positive 384 L to the power 3. So this minus 1 over 384 L squared is your C3, and 1 over 384 L cubed is your C4. Alright, and obviously your C1 is this term here, and your C2 is 0. So what I was going to do before I finish this, again, all of this page is unnecessary. I will just check my final answer. So I will check by looking at this equation and seeing whether it equals 0 when when x equals L. So let's do x equals L first. So we've got a minus 1/8. Then we've got a plus 1/8. Then we've got a minus 1684. Yeah, you can see that it does work. Plus 1384. So that equals 0. And then the other one to check is, does this equal 0? No, not does it equal 0. Oh no, that's what I can do to check it, isn't it? The other thing I can do to check is, what's the value when we are at L over 4? Right, so what does that value equal? So let's substitute that into equation 2 and into equation 1. So equation 2 gives me minus 1/8 times by a quarter to the power 3 plus 1/8 times by a quarter to the power 2 minus 1/384 times by a quarter plus 1/384. So I've substituted in those values all into these values using my calculator to do the work, and it says that I get a 1/128. So now let's see if that matches for equation 1. So here we're now substituting quarters into here and here and see what we get. So 1 divided by 24 times by 0.25 to the power 3 plus 11 divided by 384. So that's effectively 1. And here we want to substitute in a quarter. And we get 1/8/4. So that's equation 1. So actually I'm quite happy that that solution seems to be perfect. Okay, so that's equation question 2 done. And then I said, everything on this page you don't have to do. Don't worry about it. It was just me being me. All right.